Come on, my dears, we proceed further in chapter number 1. Come on, question number 22. It is about pictorial presentation of electric field. Look, surrounding to every electric charge, we know it has its own electric field, correct? And you also know that electric field is not simply an imagination, it is also a reality, okay? So when we know that electric field definitely exists around electric charge, then let us try to exhibit, let us try to show it in the diagram. Whenever you want to show electric field in the diagram, means whenever you want to have pictorial presentation of electric field, you can have three methods to show electric field in the diagram. You can either use electric field vectors, or you can use electric field lines, or you can use equipotential surfaces. Okay, I repeat, you can show electric field by three methods. You can take the help of electric field vectors, or electric field lines, or equipotential surfaces. So far electric field vectors are concerned, we will study right now. Electric field lines we will study later on, and this equipotential surfaces we will study in chapter number 2. Okay, fine. Now first of all, let us define what is called electric field vector. Look, electric field vector is that vector whose length is directly proportional to magnitude of electric field and which is always shown in the direction of electric field. Such a vector is called electric field vector. I repeat, a vector whose length is or whose magnitude is directly proportional to magnitude of electric field and whose direction is in the direction of electric field is called electric field vector. Okay. So now we would like to show electric field using electric field vectors. For example, if you want to show electric field of a positive point charge, then how would you show it? You can show that electric field by the electric field vectors as shown in the diagram. Have you noticed one thing? As you move away from the charge, in any direction, then the length of electric field vector decreases. Why? Just now I told you that length of electric field vector is to be shown directly proportional to magnitude of electric field. And don't you know, for a point charge, what is electric field? Kq upon r square. Electric field of a point charge is inversely proportional to square of the distance. So as distance would increase, electric field will decrease. As you move away, distance increases, so electric field will decrease. That's why you must show gradually shorter and shorter arrows. Okay, fine. What about direction? So far direction of electric field at any point is concerned, you know it is always in the direction of resultant Coulombian force exerted on a test charge. Suppose you want to find out direction of electric field at this very point, then at that point you should imagine a test charge, and test charge is always positive. So if given charge is positive, positive will repel positive, so Coulombian force will be exerted in this direction, and so in the same direction you will take direction of electric field. So at this very point, direction of electric field is like this, correct? Similarly at this point like this, okay, at this point like this, fine. So what have you noticed? For a positive point charge, direction of electric field is always away from it, okay, fine. Now you talk about negative point charge. For a negative point charge, you can just show the arrows like this only, but have you noticed one change? So far direction of electric field is concerned, now the directions of arrows are reverse. Earlier it was away from positive charge, now it is towards negative charge. Why towards negative charge? Because if you want to find out direction of electric field, say at this point, you should consider test charge at this point, and test charge is always positive, and this negative charge would attract that positive charge this way. So at that time, direction of Coulombian force will be like this, and if direction of Coulombian force is this, then in the same direction there is direction of electric field. Have you noticed that all these arrows are pointing towards this negative charge? Okay. For a positive charge, electric field is away from it. For a negative charge, electric field is towards it. And here also, as distance increases, the magnitude of electric field decreases. That's why as you move away from the negative charge, you must show gradually shorter and shorter arrows. Okay, take care. I repeat, you can show electric field pictorially either by using electric field vectors or by using electric field lines or by using equipotential surfaces. Okay, using field vectors, how you can show the electric field, just now I have shown. Okay, using field lines, how you can show electric field, we will study later on in the same chapter, and regarding equipotential surfaces we will study in next chapter. Got it? We now go for question number 23. Electric dipole. Here is an electric charge system consisting of 2 point charges equal in magnitude, opposite in polarity, and charges are separated by some finite distance. Such an electric charge system is called an electric dipole. A system of 2 point charges with equal magnitudes but opposite polarity separated by finite distance is called an electric dipole. Right? A system of 2 point charges with equal magnitudes and opposite polarity but separated by some finite distance is called an electric dipole. Got it? Fine. Here is negative charge of that dipole. Here is positive charge of the dipole. Di means 2, pole means polarity. There are 2 polarities. One is negative, another is positive. Correct? Now, these 2 charges are separated by this much finite distance, and let it be 2a, where a indicates distance of either charge from the midpoint of the dipole. When this distance is a, this is also a, totally it is 2a. Correct? Fine. Now for this electric dipole, we would like to have some measure of its strength. The measure of strength of electric dipole is given by one vector physical quantity called electric dipole moment. Electric dipole moment. And that electric dipole moment is shown by symbol vector P. Electric dipole moment is shown by symbol vector small p. And how is it defined? I am showing you. It is defined by such a product where Q is the magnitude of either charge and 2a is the distance between 2 unlike charges. Correct? Fine. Product of magnitude of either charge in a given electric dipole and distance between 2 unlike charges is called electric dipole moment of a given dipole. I repeat, product of magnitude of either charge in a given electric dipole and distance between 2 unlike charges is called electric dipole moment of that dipole. Correct? Fine. Now, so far direction of vector P is concerned, it is always taken from negative charge to positive charge. From negative charge to positive charge. You can see this arrow. Correct? From negative to positive. Okay? Let us find out now its a unit. Come on. Unit of this will be unit of this and this. Unit of charge, come on, coulomb, and unit of distance is meter. Unit of charge is coulomb, unit of distance is meter, coulomb into meter, coulomb into meter. Symbolically you may write capital C, small m. It is not centimeter, it is coulomb into meter. Capital C stands for coulomb into meter. Okay. What about total charge of electric dipole? Total charge is 0 because it is minus q plus q. minus q plus q. When you make algebraic summation of these two charges, the total comes out to be 0. Now, when total charge is 0, you may think that this dipole will not have any electric field because there is no total charge, but it has electric field. Why? Because no doubt total charge is 0, but two constituent charges are not located at the same position. They are separated by some finite distance. Okay? Because the two charges are located at two different positions, this dipole has electric field. Surrounding to any electric dipole, at every point in the surrounding region, we have some electric field. It is a speciality of this electric dipole that surrounding to electric dipole, it has its electric field at every point. There is not a single point where electric field of dipole is 0, correct? There are no points where electric field is 0. At every point surrounding to electric dipole, it has some electric field. Okay? Now, we go for what is called point dipole. What is called point dipole? A dipole in which the magnitude of either charge tends to infinite and distance between two unlike charges tends to 0. Such a dipole is called a point dipole. An electric dipole in which magnitude of either charge tends to infinity and distance between two unlike charges tends to 0 is called a point dipole. In short, if you have got enormous amount of charges and very close to each other, then it will form a point dipole, correct? A point dipole is that in which charge tends to infinity and distance tends to 0. Okay, fine. Now, for a point dipole, we would like to determine its electric field at some point on its axis and at some point on its equator. Now, first of all, what do you mean by axis? What do you mean by equator? Let us see. We now go for question number 24. To find electric field at an axial point outside the dipole. Okay, I am showing you. Consider this as electric dipole in which this is negative charge minus q, this is positive charge plus q, and this vector I have shown here from negative charge to positive charge, it is nothing but electric dipole moment shown by symbol vector small p. Fine. In the figure, this dipole is shown such that its midpoint coincides with the origin of coordinate system and the axis of this dipole coincides with a z axis. What do you mean by axis of a dipole? Very simple. A line passing through two charges of a dipole is called an axis. Come on. This is the line passing through these two charges, correct? Passing through these two charges, this is the line, and that very line is called axis of dipole. Then what do you mean by an equator? An equator is perpendicular bisector of an axis. Come on, perpendicular to this axis and passing through midpoint of this dipole is this line, and that line is called an equator. An equator. A perpendicular bisector of axis of dipole is called its equator or equatorial line. Okay, fine. Now, can you tell me how many axes would be there? How many equatorial lines would be there for any electric dipole? Can you tell me? Try to imagine. Every electric dipole has only one axis, but infinite number of equatorial lines. How? I am showing you. Suppose this is the axis of a particular electric dipole. Here you may consider negative charge, here you may consider positive charge, correct? And as I told, a line passing through two given charges in a dipole is called its axis. Okay. So, this is now axis. Then what do you mean by equatorial line? It is a perpendicular bisector, Now, you may consider this as equatorial line. Suppose you are drawing perpendicular bisector towards your right hand side this way, correct? But not necessary that you must draw towards right hand side only. You may think of a perpendicular bisector towards you this way, correct? Towards me, then this way, correct? So, I mean to say, if you take this as perpendicular bisector, it becomes equatorial line, and now you may rotate it this way. Look here, this way, correct? All these lines are perpendicular bisectors for the axis. These all lines are perpendicular bisectors, correct? And they are number wise infinite, correct? You may think of a plane, correct? Horizontal plane which is perpendicular to vertical axis, and not only that, that plane should pass through midpoint of the dipole. And now in that plane, if you think of equatorial lines, those equatorial lines can be considered like this, correct? Like this. So, I mean to say equatorial lines will be infinite in number. Let me show it in the diagram now. Look. Here is horizontal plane which is perpendicular to this axis of dipole. This is negative charge, this is positive charge. So, this is axis now, and now all these are lines which are passing through midpoint of the dipole and perpendicular to this axis. They are all equatorial lines, and such equatorial lines number wise you can consider infinite. Okay, fine. Now, in this question we have to find out electric field of an electric dipole at some axial point, but that point we must select outside the dipole. Look here. This is the axis now, this is the dipole, and outside the dipole at this very point I have considered the point of observation where I am interested in finding out electric field, that is point P. And distance of point P from the midpoint of the dipole I am taking as Z. Okay, fine. Now, you know distance between these two charges, it is 2a. So, distance of either charge from midpoint it is a, distance of this charge from midpoint again it is a. Now, tell me, in this direction there is dipole moment vector small p. In the same direction I define one unit vector which is p hat, correct? P hat is unit vector in the direction of electric dipole moment vector. Okay, fine. Now, you want resultant electric field of the entire dipole at this very point. For that, what you should do? You should find out independent electric fields produced by these 2 point charges at this very point, and then after you should go for vector addition, correct? Then you get resultant electric field. But so far this positive charge is concerned, it is a point charge, and for a point charge, don't you know electric field, it is kq upon r square. Just pick it in words, k into charge upon distance square. Look here, this is vector E positive, that is electric field at point P due to positive charge. Okay, as I said, it is k into charge upon distance square. K into charge, magnitude of charge is q upon distance square. Look, this much distance is z, correct? And this much distance is a. So, what is this much distance? Distance of point P from this positive charge would be this much, and that distance would be z minus a. Z minus a, and the distance square, okay? And multiplied by unit vector, because here I am writing vector sign, okay? Vector equals to magnitude multiplied by unit vector. Come on, at this very point, what will be the direction of electric field produced by this positive charge? Just now I told you in this question, for a positive point charge, direction of electric field is always away from it. So, at this very point, direction of electric field produced by this point charge would be away from it, will be this way, correct? Away from this charge, this way. This way means what? In the direction of vector small p, correct? And in the direction of vector small p, what is the unit vector? Unit vector is p hat. That's why I am multiplying by p hat. Okay? Vector equals to magnitude multiplied by unit vector. Okay? Similarly, what will be electric field at this very point due to negative charge? I am showing it by symbol vector E negative. Okay? Again it is kq upon r square, just speak it in words, k into charge upon distance square, k into magnitude of this charge, magnitude of this charge is also q only, divided by distance square. Distance of this point from this very charge would be, come on, this much distance, correct? It is this z plus this distance, this is a. So total distance of this point from this negative charge would be z plus a, and its square, okay? K into charge upon distance square and multiplied by unit vector. Now take care, vector equals to magnitude multiplied by unit vector. Come on, so far direction of electric field at this point is concerned, produced due to negative charge. You must have remembered, here I told you, direction of electric field produced by negative charge is always pointing towards negative charge. So at this very point, direction of electric field produced by this negative charge would be towards it, like this, correct? Like this. Towards this charge means like this. Like this means what? Opposite to this vector p. Opposite to vector p. Opposite to vector p. So you must take here unit vector which is opposite to p hat. Opposite to p hat, that unit vector is minus p hat. Okay, fine. Vector equals to magnitude multiplied by unit vector. Now I want resultant electric field at this very point. Let it be shown by symbol vector E into bracket, you should write z, just to indicate that this is a function of z. This is a function of z. Okay, fine. Now that resultant electric field can be found out by making vector addition of these two independent electric fields. Come on, vector E positive plus vector E negative. Okay, come on, take this plus this. When you take this plus this, it will be this plus this. Okay, fine. Now when you take this plus this, which part you can take common? K into q and p hat, that much part you can take common. K into q and p hat you can take common. K into q and p hat I have taken common. What is left inside the bracket? From here 1 upon z minus a whole square, 1 upon z minus a whole square. From here minus 1 upon z plus a whole square, minus 1 upon z plus a whole square. Okay. This kq as it is. Now when you take LCM, it will be this into this, I have written here. This part will be multiplied here, this part will be multiplied here. Come on, z plus a square will come here. Come on, expand, z plus a square. What is expansion? Z square plus a square plus 2za. Z square plus a square plus 2za, correct? Z minus a square will come here. Z minus a whole square will come here. So what is the expansion of square of z minus a? Z square plus a square minus 2za. But here outside it is minus sign. Come on, minus z square minus a square minus minus plus 2za, correct? Divided by, in the LCM it will be this into this. Come on, z plus a square into z minus a whole square, correct? Into p hat as it is, fine. Now just simplify, kq as it is. Come on, z square minus z square will cancel, a square minus a square will cancel, 2za plus 2za, totally it is 4za, correct? In the denominator, if it is z plus a into z minus a, what is it? Z square minus a square, but here it is square, so I should write z square minus a square whole square, correct? This p hat as it is, fine. And now let me rearrange this. Instead of 4, I just write 2 into 2, correct? This k as it is, q as it is, this a as it is, and z also as it is, okay? P hat as it is, denominator is also as it is. Okay, I just splitted 4 as 2 into 2, no problem. And why I have put this term in bracket 2a into q, you must have come to know. If you take magnitude here, P equals to 2a into q, P equals to 2a into q, that is electric dipole moment. So in place of 2a into q, I can write electric dipole moment, that is small p. Just write it here, 2kpz. Come on, 2kpz upon z square minus a square whole square, z square minus a square whole square into p hat, correct? This is the general formula for finding electric field at any axial point outside the electric dipole. Okay? But now we go for one specific case, one special case. What is the special case? For very far axial point. If you take point on axis outside the dipole, that is true, but very far, then this point P is taken very far, then this distance Z would be very much greater than this distance A. If Z is very much greater than A, further Z square will be very much greater than A square. If Z square is very much greater than A square, then in this term, because A square is negligibly small terms can be neglected in comparison with magnitudes with other terms in addition and subtraction. If A square is negligibly small, we can neglect it in this subtraction or addition. So if you neglect A square because it is very small, then left out is only Z square. So Z square minus A square can be replaced by only Z square. Just replace it here. In this denominator, if you neglect A square, then left is only Z square and its square, that is Z raised to 4. In the numerator there is 1Z, in the denominator Z raised to 4. So 1Z will be getting cancel. So ultimately 2kp upon Z cube. What is left out? 2kp upon Z cube. 2kp upon Z cube. This P hat I have written as it is. This vector E as a function of Z I have written as it is. Okay. Now take magnitude on both the sides. When you take magnitude here, it is E. When you take magnitude here, it is 2kp upon Z cube. And when you take magnitude of a unit vector, it is 1. Where I am writing EA, A should be written as a suffix just to indicate that this is the electric field on the axial point, okay. For a given electric dipole, this dipole moment is constant, K is as such constant only. So this is inversely proportional to Z cube. This electric field is inversely proportional to Z cube means it is inversely proportional to cube of the distance of axial point. But which axial point? Very far axial point. Okay. Tell me, can you say from this expression that electric field is a characteristic presentation of its source? Definitely. If you have electric field which is inversely proportional to square of distance, it must be of point charge. Here it is inversely proportional to cube of distance, it must be of electric dipole. So from electric field we can recognize whose electric field is like this, correct? You can just identify its source. If we can identify the source of electric field, then we can say electric field is nothing but a characteristic presentation of its source. Okay, fine. Come on, now we go for question number 25. To find electric field at an equatorial point of electric dipole. Just like previous question, here also we consider electric dipole in such a manner such that its axis should coincide with Z axis and its midpoint should coincide with the origin of coordinate system, correct? Fine. This is negative charge minus q, this is positive charge plus q. Distance of either charge from the midpoint of dipole is small a. This is also small a, correct? Total distance between these two charges would be a plus a, that is 2a. Got it? What about electric dipole moment? It is always to be shown in a direction from negative to positive charge. From negative to positive charge, this way. Correct? and that is shown by symbol vector small p. In the same direction, I have also shown one unit vector in the diagram, and that unit vector is small p hat. Okay, p hat is the unit vector chosen in the direction of electric dipole moment vector. Got it? Fine. Now, if this is axis, then this is perpendicular bisector for that axis. It is nothing but an equatorial line, and right now that equatorial line I just take it as y axis. Okay, just select one point, say point Q, on this equatorial line, which is at distance small y from this origin. Okay, now at this point, which is on the equatorial line, I would like to find out electric field produced by entire dipole. How would you find out? Again, you should find out independent electric fields produced by these two charges, and then you should make vector addition. Okay, come on. Electric field due to positive charge, E positive. Okay, I am writing here only magnitude. Come on, magnitude of electric field produced by a point charge in words k into charge upon distance square, k into charge upon distance square, k into charge is q upon distance square. Come on, find out distance of this point from this charge. Find out this distance. Come on, this much distance is y, this much distance is a. This is the right angle. Come on, apply Pythagoras theorem. This will be hypotenuse, and for hypotenuse, what is the measurement? Come on, square root of summation of squares of remaining two perpendicular sides. So it is under root of y square plus a square. Correct? But now, in the formula, we have to write k into charge upon distance square. So square of this, then square root will vanish, giving you y square plus a square. Correct? Similarly, electric field produced due to negative charge at this very point. Come on, E negative. Again it is k into charge upon distance square. K into charge. Here also we are writing magnitude here. So take magnitude of this. Again it is q. And whatever is this distance, same is this distance. Correct? So if this is under root of y square plus a square, this also will be under root of y square plus a square. And it's a square. So I should write y square plus a square. K into charge upon distance square. Got it? Fine. Now what about direction? Direction of electric field at point Q due to positive charge. Don't you know, for a positive charge, direction of electric field is away from it. So away from this means like this. Correct? In this direction. It is E positive. Okay? Fine. And what about direction of electric field produced due to this negative charge? For a negative charge, electric field is in the direction towards the negative charge. So at this very point, it is towards this negative charge this way. Correct? Fine. So I am writing here E negative, which is pointing in this direction. Fine. For a positive charge, away from it. For a negative charge, towards it. Fine. So far magnitudes of these two are concerned, magnitudes are equal, because whatever is the magnitude of this charge, same is the magnitude of this charge. Whatever is this distance, same is this distance. Okay, fine. If these two magnitudes are equal, I may show it by common symbol. Let it be E dash. Okay, fine. Now just take this angle as theta. If this angle is theta, this also is theta. Corresponding angles, how? If these two are vertical lines, means both of them are parallel, this is transversal, and then if these two are parallel lines and if this is transversal, these two angles will be corresponding angles, they have to be equal. So if this is theta, this also is theta. Now just resolve this vector into two mutually perpendicular components like this. This vector plus this vector. Come on, this plus this will give you this vector. Correct? Now similarly this also can be resolved into two mutually perpendicular components, this vector plus this vector. Okay? Come on. For this component, what would you say? Component of E dash adjacent to theta. Component of E dash adjacent to theta. What is it? E dash cos theta. Component of E dash opposite to theta. What is it? E dash sin theta. Come on, similarly here, component of E dash adjacent to theta, it is E dash cos theta. Component of E dash opposite to theta, it is E dash sin theta. Now you can see these two components which are E dash sin theta each, they are equal in magnitude, opposite in directions, so they will nullify the effect of each other, they would cancel each other. Fine. Then whatever electric field will be produced at point Q, it is solely due to E dash cos theta components. And because both the components are pointing in the same direction, whenever vectors are in the same direction, you can make a scalar addition, correct? So what will be total electric field at this very point Q? It will be summation of these two. Come on, summation of these two, E dash cos theta plus E dash cos theta, total it is 2 E dash cos theta, correct? So magnitude would be 2 E dash cos theta. And now electric field at point Q, which is a distance y from midpoint of the dipole, I just show it by this symbol, vector E as a function of y, it is magnitude wise 2 E dash cos theta, this plus this, just now I told you, this plus this, correct? 2 E dash cos theta, but don't you know vector equals to magnitude multiplied by unit vector. Now take care, direction of this electric field is in the direction of these components, because electric field is right now produced due to these components. But where are these components? Pointing downwards. Downwards means what? Opposite to P hat. Opposite to P hat. Opposite to P hat, that's why I must multiply by minus P hat. You must write that unit vector which is in the direction of this component, but these components are in the direction opposite to P hat, that's why I am writing here minus P hat. Okay, vector equals to magnitude multiplied by unit vector. These two as it is. What about E dash? E dash is nothing but E positive. E positive is, come on, KQ upon Y square plus A square. KQ upon Y square plus A square into cos theta, into cos theta. Come on, in this right angle triangle, what is cos theta? Adjacent to theta divided by hypotenuse. Adjacent to theta, it is small a, divided by hypotenuse opposite to right angle, it is under root of y square plus a square. Come on, adjacent side divided by hypotenuse, hypotenuse is y square plus a square whole raised to 1 by 2. Whenever you see square root sign, the power is 1 by 2, correct? This minus P hat as it is, fine. And now tell me, can you rewrite K into 2A into Q, K into 2A into Q, here it is. K into 2A into Q, and the denominator, come on, y square plus a square, here power is 1, y square plus a square, here power is 1 by 2, whenever base is same, in multiplication, whenever base is same, addition of powers, 1 plus 1 by 2, that is 3 by 2, correct? And this unit vector minus P hat as it is, fine. And now this symbol as it is, but K as it is, and now 2A into Q, don't you know? What is 2A into Q? Product of magnitude of either charge in a given electric dipole and the distance between two unlike charges in that dipole is known as electric dipole moment of the dipole, shown by symbol small p. Come on, in place of 2A into Q, you may replace it by small p, and here denominator as it is, minus P hat as it is. This gives me general formula for finding electric field at any equatorial point of electric dipole. Okay, this is general formula, but now we go for a special case. What is that special case? At very far equatorial point, instead of taking this point Q over here, you may take it very far. If you take it very far on the equatorial line, then this distance y would be very much greater than a. If y is very much greater than a, further y square will be very much greater than a square. Then in this addition, y square plus a square, if a square is negligibly small, you may neglect it safely in addition. Okay, if you neglect a square, then this addition is as good as y square. Come on, here in the denominator, if a square is negligibly small, if you neglect, then left out is y square whole raised to 3 by 2. When you multiply these two powers, 2 will cancel, giving you y cube in the denominator. So ultimately Kp upon y cube into minus p hat. Kp upon y cube into minus p hat, correct? Now tell me, this is not a general formula, this is a special case. You can use this formula only for finding electric field at very far equatorial point, okay? Now take magnitude. When you take magnitude, here it is E, I am writing, E stands for equator, and when you take magnitude here, Kp upon y cube, magnitude of unit vector is 1, okay? When these two are constants, what about relation of this with this? E inversely proportional to y cube. This electric field at very far equatorial point is inversely proportional to cube of distance, correct? Once again let me tell you, if you have electric field which is inversely proportional to square of distance, it must be of a point charge. If you have electric field which is inversely proportional to cube of distance, it must be of electric dipole. So this is how from electric field we can come to know about its source. That's why we say many times electric field is nothing but a characteristic presentation of its source, okay? Let us discuss now extra point number 5. What is the extra point? You just do one thing. You take 2 points, one on axis, one on equatorial line for electric dipole. But you please take those 2 points very far, but at equal distances from midpoint of the dipole. So if you select 2 points, one on axis, one on equatorial line, very far and at equal distances from midpoint of the dipole, then let us make comparison between the electric fields. I am showing you. What is electric field at very far axial point? At very far axial point, EA equals to 2 Kp upon Z cube. Come on, 2 Kp upon Z cube, okay, fine. What about electric field at very far equatorial point? Kp upon Y cube, correct? But as I said, you are supposed to take those 2 points not only very far, but at equal distances from the midpoint of the dipole. If these 2 distances are equal, let them be shown by symbol small d. Z equals to Y equals to d. So in place of Z also you can write d, in place of Y also you can write d. Come on, in place of Z when you write d here, it is d cube. When you write here in place of Y d, then it is here d cube. Come on, wherever it is Kp upon d cube, we can write EE. Come on, write it here. Kp upon d cube can be replaced by EE. So this is replaced by EE, this 2 as it is, this EA as it is, correct? A for axis, E for equator, correct? Come on, how would you express this result in words? For very far equidistant points, one on axis and one on equatorial line for electric dipole, it is found that electric field at the axial point is double than electric field at the equatorial point, okay, fine. My dears, here one more point. Have you seen the distribution of electric field vectors in different directions? Can you see spherical symmetry? Whatever is the distribution towards right hand side, same is the distribution towards left hand side. Whatever is the distribution in upward direction, same is the distribution in downward direction, like that. I mean to say, if you consider this charge at center of some sphere, then these arrows are lying on some spherical surface, okay. That's why we say this electric field of a point charge has spherical symmetry, okay. Similarly, electric field of a dipole, it is having cylindrical symmetry, These words are not used in the textbook, just for your kind knowledge, okay. The electric field of a point charge is having spherical symmetry, whereas electric field of electric dipole is having cylindrical symmetry, okay, just remember. Come on, my dears, let us see now question number 26. See the title, torque exerted on electric dipole placed in uniform electric field. First of all, tell me what is called uniform electric field. Uniform electric field is that electric field in which intensity remains constant throughout. At every point, intensity of electric field must be same. Okay? It should not change with position, it should not change with time. Okay? It should remain constant. Okay? Such an electric field is called uniform electric field. Just to show that uniform electric field in the diagram, we take the help of electric field vectors, but those field vectors you must show them as shown in the diagram. Look, just to show uniform electric field by electric field vectors, you must show all those vectors mutually parallel. Not only that, the perpendicular distance between each two consecutive field vectors must be shown same. Okay, fine. Now, in this uniform electric field, we just place one electric dipole having electric dipole moment vector small p, making angle theta with a uniform electric field. Okay. Just for the sake of convenience, we have chosen the midpoint of electric dipole placed at origin of Cartesian coordinate system. Okay. Let this right hand side axis be positive x axis, let this be positive y axis. I mean to say, a plane passing through x and y axis, which is xy plane, it is nothing but surface of board, or you can say it is plane of figure, plane of figure. Okay, fine. Now, in this dipole, there are two electric charges equal in magnitude, opposite in polarity. One is positive charge, say plus q, another is negative charge, minus q. Okay. Now tell me, on this positive charge, what this electric field will do? Will provide electric force. I told you to remember formula of electric force in words. What was that formula? Electric force equals to charge into electric field. Charge into electric field. Here charge is q and electric field is vector E. Correct? Fine. Let it be vector F1. It is electric force exerted on first charge. What about this second charge? Let it be vector F2. Again, come on, electric force means what? Charge into electric field. But charge is minus q. Correct? Charge is minus q. Into electric field is vector E. Correct? Now tell me, why it is shown in this direction? Very simple. What does this negative sign indicate? Negative sign indicates that these two vectors are in opposite direction. If vector is toward right hand side, then this force must be shown towards left hand side. Okay. Here there is a positive sign, so these two vectors are in the same direction. Here there is a negative sign, so these two vectors are in just opposite directions. Now onwards, please remember one thing. On a positive charge, electric force is exerted in a direction of electric field. But on a negative charge, electric force is exerted in a direction opposite to electric field. Okay, fine. Now, these two forces have equal magnitudes. So, you must show these two arrows with the same length. Okay, but they are in opposite directions. Not only that, their lines of action are different. Line of action of force means that line which passes through the force vector, which passes through the force vector. So, passing through this force vector is this line, which is called line of action of force F1, and passing through this force vector, that line is this, which is nothing but line of action of vector F2, correct? These two lines are different lines. So, these two forces are non-collinear, correct? They are not collinear, And when you have two forces equal in magnitude, opposite in directions, which are not collinear, definitely they will produce some torque, and that torque we have to find out. Okay, let us find out. The resultant torque exerted on entire dipole, I am taking by symbol vector tau. Okay, and remember one more thing, as many forces that many torques, as many forces that many torques. Here there are two forces. Okay, so there must be two torques, and if I am making vector addition of those two torques, I must get resultant torque, correct. So vector tau equals to vector tau 1 plus vector tau 2, and you have studied in 11th standard what is formula for vector tau, vector r cross vector f. So for vector tau 1 you may write vector r1 cross vector f1, correct. Similarly for vector tau 2 it should be vector r2 cross vector f2, correct. Now with respect to origin, the position vector of first charge I just show it by symbol vector r1, and you know distance between two charges in electric dipole, it is 2a. This length is half of 2a, half of 2a means a, and let this vector be vector small a, correct. Similarly position vector of second charge with respect to origin is in this direction, and let it be vector r2. It is just opposite to vector a, so I am writing minus of vector a, minus of vector a. Okay, come on, put up the values. Vector r1 is nothing but vector a cross vector f1 is nothing but q into vector e, q into vector e, correct, plus vector r2 is minus vector a cross vector f2 is minus q into vector e, minus q into vector e. Got it? Fine. Now this vector a cross q vector e as it is, but here minus plus vector a cross q vector e. Now same term is repeated twice, so I can just multiply by 2. So 2 into vector a cross q vector e, 2 into vector a cross q vector e, correct. Fine. Now here q is charge, which is scalar quantity. You may multiply with vector e, and then instead of multiplying with vector e, if you multiply here, that also will do. Instead of multiplying q with vector e here, you may multiply q with this vector here, no problem, it does not make any difference. So I am writing 2 into vector a into q cross vector e, correct. So here order of cross product I am not changing, I am shifting the position of q. Instead of multiplying with vector e, I just multiplied with this vector. Okay, fine. Now you must have come to know why I did like that. You know, product of magnitude of either charge in an electric dipole and the distance between two unlike charges in the dipole gives us, come on, electric dipole moment. So this product will give me electric dipole moment. Let it be vector small p cross vector e. So what is the final formula? Vector tau equals to vector p cross vector e. Vector tau equals to vector p cross vector e. Got it? Fine. If you are interested in finding out magnitude, you may take magnitude on both the sides. So when you take magnitude here, it will be tau. When you take magnitude here, it is p is sin theta. P is sin theta. What is theta? It is angle between vector p and vector e. This theta is angle between vector p and vector e. Okay, fine. Now let us find out direction of vector tau. How would you find out direction? Direction of vector tau means direction of vector p cross vector e, correct? And how would you find out direction of any vector product? Using law of right-handed screw. I am showing you how to find it. Look, say this is vector p, correct? And this vector e, I just take it this way. So situation is like this. This is vector p, dipole moment vector. This is vector e, electric field vector. And this is the angle theta between them, correct? Now, in order to find out direction of vector p cross vector e, what you must do? you must think of a plane passing through these two vectors, correct? So think of a plane passing through these two vectors, which is nothing but surface of board, and then after you must consider a right-handed screw which is placed perpendicular to that plane like this, and then after you are supposed to rotate this right-handed screw in a manner first vector rotates towards second vector. In this order, first vector is vector P, and that vector you must rotate towards vector E. So when vector P is rotated towards vector E this way, through the angle between them, the manner of rotation is this way, correct? This way. In the same manner, I must rotate this right-handed screw. Now, if this right-handed screw is rotated this way, correct, then it will go inside. It will go inside. And if it goes inside, then direction of vector tau, you can say it is going inside the plane of the figure perpendicularly. Going inside the plane of the figure perpendicularly, correct? That's what I am writing here. Perpendicularly inside the plane of the figure. Perpendicularly inside the plane of the figure. In physics, there is a custom, there is a tradition. If any direction is inside the plane of the figure perpendicularly, it must be shown by a symbol of cross. And if the direction comes out of plane of figure perpendicularly, you must show it by symbol of dot. Here it is perpendicularly inside, so I just show it by symbol of cross. Okay, fine. Now naturally, when torque is exerted, what will happen? When torque is exerted, what will happen? This dipole will start rotating under the influence of the torque, but it will rotate this way, correct? It will rotate this way. When vector P is approaching vector E this way, ultimately what will happen? Theta will decrease. Theta will go on decreasing. At one stage, this vector P will become parallel to vector E. When vector P becomes parallel to vector E, come on, theta is 0 degree. And when theta is 0 degree, sine 0 is 0. That's why tau will be 0. Tau will be 0. Come on, place theta equal to 0 here. Then sine 0 is 0. So tau will be 0. And when tau is 0, meaning thereby in this situation, in this condition, there is no torque exerted on this dipole, and hence it would prefer to remain in the same condition without rotation, correct? And if this dipole remains parallelly aligned with vector E, then this is the stable equilibrium condition. Why it is stable equilibrium condition? Because dipole prefers to remain in this state. And why it is equilibrium condition? Because it is at rest, okay? At rest, then we say equilibrium condition, and dipole prefers to remain in this condition. We call it stable equilibrium condition, okay? Now consider this case. Suppose you are aligning vector P just opposite to vector E, okay, anti-parallel. If vector P and vector E, both of them are in opposite direction, then angle theta between them will be 180 degree. When you write theta equals to 180 degree here, sine 180 will be 0, and again torque will be 0. So when torque is 0, at that time it is said to be in equilibrium condition because it will lie at rest, but we call it unstable equilibrium condition. Why unstable? Because in this condition, if you just disturb this dipole slightly, again it will be getting aligned parallel to vector E by itself, okay, because it is stable equilibrium condition. But here it so happens, if you disturb this dipole slightly, then it never comes in this position once again, never. On the contrary, what happens? That it comes in this condition, okay. So this is unstable equilibrium condition, unstable equilibrium condition, because once you disturb this dipole, it does not come back in the same condition, okay, fine. I can make you realize or understood with this stable and unstable equilibrium condition very nicely by giving a very good example. Consider this small sphere, say a ball bearing, okay. This small spherical ball, it is placed in this bowl, okay. Now this sphere, if you disturb it slightly, then ultimately it comes at the same position, it comes in the same condition. It comes at the lowest height, because at that height its gravitational potential energy becomes minimum, okay. So this is called stable equilibrium condition. And if you consider a sphere just at the top of this bowl, placed this way, then as long as you don't disturb this, it will remain steady. Okay, that's why it is equilibrium condition. But it is unstable equilibrium condition, because if you disturb this ball slightly, then it will simply fall down this way or this way. It will never come back in the same condition. Correct? So this is unstable equilibrium condition. This is stable equilibrium condition. Correct? Marble inside a bowl, marble on the top of the bowl, marble inside the bowl, and marble on the top of the bowl. Okay, fine. And third case, come on, maximum non-equilibrium condition. Maximum non-equilibrium condition. Consider an electric dipole which is placed at right angle to the electric field, and then angle between vector P and vector E is right now theta equals to 90 degree. Place theta equals to 90 degree here, sin 90 degree is 1, and for sine function, when you are writing 1, it is its maximum value. When this sine function is maximum, naturally torque will be maximum. That's why I am writing tau maximum. Correct? And when you write 1 here, 1 into PE, that is P into E. Okay? So when maximum torque is exerted in this condition, naturally this dipole will not remain in that condition even for a fraction of second. Immediately it would take a turn. I mean to say, it indicates maximum non-equilibrium condition. Why non-equilibrium? Because it does not remain steady in the same condition. Correct? And maximum, because maximum torque is exerted. That's why. Got it? One more thing. If the dipole is lying parallel to vector E, and then after again you want to bring it at angle theta with vector E, then you need to rotate it. And when you want to rotate it, naturally you have to exert some external torque. And at that time, what this electric field is trying to do? Electric field is trying to rotate that dipole back in the same condition. Correct? Electric field is exerting torque this way, and you want to rotate the dipole this way. So at that time you will require to do some work against the restoring torque developed by electric field. Okay? And at that time, when you want to do that work, you have to spend energy, and at that time whatever energy is spent by you, it is getting stored in that electric dipole in the form of energy which is called electrostatic potential energy of dipole in the electric field, about which we will study in the next chapter. Okay? In this process, whatever work is done by you gets stored in the form of increase in electrostatic potential energy, suppose shown by symbol delta U. Okay, fine. And in this uniform electric field, when you place this dipole, you can see these two forces are exerted equal in magnitude, opposite in direction. So what about resultant force? Resultant force is vector F1 plus vector F2. So it is Q into vector E minus Q into vector E. This becomes 0 vector. And if resultant force is 0, in 11th standard you have studied, on whichever object there is no resultant force, it is said to be in linear equilibrium condition. So at present, when you place dipole in uniform electric field, remember it remains in the linear equilibrium condition because resultant force is 0. Resultant force is 0, but in this condition resultant torque is not 0. And when resultant torque is not 0, it will continue to rotate till it becomes parallel to electric field. Okay? Once vector P and vector E are parallel, then theta becomes 0 degree. When theta becomes 0 degree, sin 0 will be 0, torque will be 0. Okay?